Imagine for a moment all these incredible AI breakthroughs we've seen lately. ChatGPT writing poetry, AlphaGo Zero just dominating games, Sora making video out of thin air. I mean, it feels like magic, right?
It really does. The pace is just staggering.
But here's the thing, the not-so-magical part.
Yeah.
All that brilliance, it takes immense energy. We're talking vast amounts of computing power to train these AIs. And, well, our traditional computers, they're actually starting to hit some serious roadblocks.
That's absolutely right. A big part of the problem is something called the memory wall. It's built into the way most computers work, the von Neumann architecture.
Okay, the memory wall.
Yeah, think of it like this. You have your computer's processor, its brain, in one room. But its memory, where all the data lives, is in a totally separate room, maybe down the hall.
Ah, okay.
So every single time the brain needs a piece of data, it has to, physically run down the hall, grab the ingredient, run back, use it, then maybe run back again to put it away. It's this constant back and forth.
That sounds inefficient.
Extremely inefficient, especially for AI, which needs tons of data constantly. It creates this huge bottleneck. And it's not just the layout, the actual silicon chips, the CMOS technology. It's bumping up against fundamental physical limits. Things like quantum effects starting to interfere and just plain old heat. They get too hot.
So if our standard computers are kind of hitting their limit, what's the alternative? I mean, what if computers could learn and adapt more? Well, more like us, like our brain.
Exactly. And that's where this really exciting field of neuromorphic computing comes in. It's all about designing systems inspired by the brain's efficiency and, its flexibility. And the key, some really remarkable tiny components.
Okay, I'm intrigued.
So that's our deep dive today. We're looking at the latest progress in neuromorphic computing, and specifically these components called memristive devices. We want to unpack how they're forming the basis for these new brain-like chips. We'll be drawing heavily on a couple of fantastic review articles. One is by Yekshao and colleagues, including Shen Gao and Zhongqing Jin from Nanjing University of Science and Technology and the Chinese Academy of Sciences. That one's in ADVI Devices Instrum from 2024.
Okay.
And the other is by Ruyu Zhao, Songju Kim, Yichun Xu, and a team including J. Joshua Yang from USC and Sandia National Labs. Theirs is titled Memristive Ion Dynamics to Enable Biorealistic Computing, and it's in a special issue of Chemical Reviews for 2025 focused on neuromorphic materials.
Got it. So our mission is to figure out how these little devices might lead to computers that actually think more like brains.
That's the plan.
All right, let's dig in. Memristive devices. Can you break that down? What is a memristor?
Okay, so imagine a tiny electronic part. It doesn't just, resist the flow of electricity like a standard resistor. It actually remembers how much electricity has flowed through it before.
So remembers.
Yeah, and based on that history, it changes its own resistance dynamically. It's like this little electronic memory keeper learning from its past. The idea itself, this sort of missing piece in electronics, was actually predicted way back in 1971 by Leon Chua.
Wow, 1971.
Yeah, but it took until researchers at HP Labs actually demonstrated it working much later. This dynamic resistance, it's not just a minor tweak, it's the key to potentially making computers learn and adapt in a more brain-like way, not just follow rigid instructions.
So it changes how computer memory even works, fundamentally.
Precisely. And what's really fascinating, and this is something J. Joshua Yang and his team really emphasized in that Chemical Reviews article, is that the secret sauce isn't just memory, it's ion dynamics.
Ion dynamics. Okay, explain that.
Right. So our brains, biologically, they compute by moving ions, charged atoms like sodium, potassium, calcium, flowing across membranes in our neurons. That's how signals happen.
Okay, yeah. Biology class, flashbacks.
Exactly. But traditional electronics, they're all about electrons moving through wires. These ion-based memristive devices, or IMDs, they actually leverage the movement of ions, just like the brain does.
Ah, so it's using the same fundamental carriers of information as biology.
You got it. And because they work using ions, they can mimic these complex, sort of lifelike biological behaviors much more naturally and efficiently than just trying to force silicon transistors to do it. It's a different starting point.
Okay, that makes sense. Instead of just electrons, they're pushing ions around. Is that the core brain-like difference?
That's a huge part of it, yeah. It's like comparing, a clockwork machine to something that actually uses chemistry. And what's even cooler is the sheer variety of stuff they're making these IMDs out of. It's not just one material.
Oh, really? Like what?
Well, Xiao and the team in these devices Instrum talk about using things like ceramics, hafnium oxide is a common one, but also flexible polymers and even, get this, biomaterials.
Biomaterials, hold on, like stuff from living things, seriously.
Seriously. And here's your wow fact, straight from Zhao and colleagues in Chemical Reviews. Imagine a computer chip component made using something literally grown in a lab.
Okay.
Researchers have actually used protein nanowires. These are harvested from a bacterium called Geobacter sulfurducens.
Bacteria wires.
Wow. Yeah. They use these tiny wires to help silver ions move, creating memristors that work at incredibly low voltages, like around 70 millivolts.
70 millivolts. Isn't that like super low? Close to biological signals.
Exactly. It's right in the same ballpark. It's almost like powering a computer chip with the whisper of a thought.
That is genuinely mind-blowing. It makes you think about, I don't know, biodegradable computers or tech that could integrate directly with our bodies. Okay, so we have these ion-moving, memory-keeping, sometimes even bacteria-powered devices. How do they actually start acting like parts of a brain?
Right, that's the key question. How do we get from device to function? We can think about it in two main ways. First, how they act like the synapses in our brain, the connections that learn and remember.
Okay, for the connections.
And second, how they can mimic the neurons themselves, the cells that process information and fire off signals.
Got it. Synapses and neurons. Let's start with synapses.
Okay, so for synaptic behavior, these memristive devices basically act as artificial synapses. Their resistance, or you can say their conductance, represents the strength of that connection. How strong is the link between two artificial neurons?
And it's not just on or off, right? You said they're dynamic.
Exactly. Unlike digital switches, which are just 0 or 1, memristors have analog memory. They can smoothly adjust the resistance to many intermediate levels. Xiao mentioned devices hitting up to 2048 distinct levels. That gives them a huge range of possible memory strength.
So they can represent very fine-tuned connections.
Right. And crucially, they mimic synaptic plasticity. That's the brain's ability to strengthen or weaken connections over time. It's how we learn.
Okay, plasticity, how does that work here?
Well, they show short-term plasticity, which lasts milliseconds to minutes, things like paired pulse facilitation or depression. If signals arrive close together, the connection might temporarily get stronger or weaker. Think about how hearing something twice quickly might make you remember it better for a moment.
Short-term memory effects.
Then there's long-term plasticity changes that last much longer, minutes to hours or even more, like long-term potentiation, strengthening, or depression, weakening.
Wow.
This is more like forming lasting memories.
Wow.
And maybe most importantly, they can implement spike timing dependent plasticity, STDP.
STDP sounds important.
It is. It's a key learning rule in the brain. Basically, it says that when a presynaptic signal arrives relative to when the postsynaptic neuron fires determines if the connection gets stronger or weaker. Timing is everything.
So the precise timing of signals actually trains the connection.
You got it. It's like the brain's ultimate timing game for learning. And these memristors, they can play that game beautifully.
That's incredible. Mimicking learning rules right down to the timing. Okay, so that's the connections, the synapses. What about the neurons themselves? The processors?
Yep, they can do that too. Beyond synapses, IMDs can emulate neuronal behaviors. They can act like simple artificial neurons, for instance, a leaky integrate and fire, or a LAF neuron.
Leaky, integrate, and fire.
Yeah, okay.
Think of it like a bucket filling with rainwater.
Yeah.
That's the integrate part. It collects incoming charge, signals from other memristors. But the bucket has a tiny leak, so charge slowly drains away over time. That's the leaky part.
Okay, I can picture that.
And if the water level of the charge builds up past a certain point, the bucket automatically tips over and sends out a splash. That's the fire part. It sends out an output spike.
Oh, I like that analogy. The leaky bucket neuron.
It captures the basics pretty well. And they can even implement more complex models. Zhao et al. Point out that you can build things like the Hodgkin-Huxley model neuron, which is much more biologically detailed, using certain types of memristors combined with other components. So we're talking about recreating not just simple neuron behavior, but quite sophisticated models too. It seems these devices are really versatile. What else can they do?
Oh yeah, they go beyond just basic synapses and neurons. For example, they can mimic aspects of dendritic computing. Dendrites are the input branches of neurons, and they do complex calculations themselves, integrating signals in space and time before they even reach the main neuron body. Memristors can help emulate that.
Adding another layer of processing power.
Exactly. They're also really interesting for something called reservoir computing. Zhao et al. Discussed this. Sometimes a single complex memristive device can act like a whole network, processing time-based signals very efficiently. Think speech recognition or predicting chaotic systems.
One device acting like a network that's efficient.
Very. And here's that twist again, hardware security. Remember how the ion movement can be a bit random, that stochasticity?
Yeah, you said it could be a challenge.
Well, you can harness it. Zhao and the team talk about using this inherent randomness to create physical unclonable functions, or PUFs. These are like unique fingerprints for chips that are basically impossible to copy, great for security and authentication, and also for generating truly random numbers.
So a potential bug becomes a feature for security. That's clever.
It really is. It turns a potential downside into a unique advantage.
But I guess that randomness, that stochasticity, does that make it harder to do, precise calculations when you don't want randomness?
That's a really sharp point. Yes, it absolutely does. Finding that balance, getting reliable, repeatable computation while maybe still leveraging the randomness for other things like security, that's a major research challenge right now. It requires careful device engineering and clever algorithms.
Okay, so we have these individual components mimicking synapses, neurons, even doing security.
Yeah.
How does it all come together in a chip? What's the big advantage then?
The big advantage comes when you build arrays of these things. Because the memristor is both the memory element and involved in the processing, you can perform computations right where the data is stored. It's called in-memory computing or processing in memory.
In-memory computing, so no more running down the hall between the brain and the pantry.
Exactly. You basically eliminate that whole data shuttle process, that memory wall we talked about at the start. The computing happens right there, within the memory array.
And that saves time and energy, I assume?
Massively. Zhao et al., in their review, specifically note that neuromorphic chips based on these principles have already shown considerably greater energy efficiency and also area efficiency, meaning they take up less space compared to standard GPUs for certain AI tasks. It's a fundamental shift, putting the processing and memory together.
Okay, so let's try and wrap this up. If someone listening today takes away just a few key things, what should they be?
Right. Okay. 3 main things, I think. First, our current way of building computers is hitting some real walls, especially with the huge demands of modern AI. We urgently need new approaches.
Okay, the need is clear.
Second, these memristive devices, especially the ones using ion movement like our brains do, are incredibly promising. They can mimic core brain functions, learning, memory processing, right down at the hardware level in a very natural way.
Got it. Ions are key.
And third, this brain-inspired approach isn't just about making computers faster. It's about making them vastly more energy efficient, which opens the door to new kinds of AI, more adaptive systems, maybe even new forms of hardware security built right in.
That potential sounds enormous. But as you mentioned, it's not all figured out yet, right? There are still hurdles.
Oh, definitely. Yeah. But it's not all smooth sailing, right? Both review articles are clear about the challenges. Things like, how do you build networks as dense and complex as the brain? How do you make sure every single one of these tiny devices behaves reliably and predictably? Getting the energy efficiency even lower, truly matching the brain's power usage, and balancing that need for stable long-term memory with the dynamic changes needed for learning. These are big engineering and science problems.
So active research areas.
Absolutely, but they're being tackled, and it's leading to this idea called co-design, where the people making the devices and the people writing the AI algorithms have to work together much more closely than before. You design the hardware and software together to get the best results.
That makes sense. Thinking about the bigger picture then, where does this all lead? Is it goodbye silicon computers?
Haha. Probably not entirely. Not anytime soon, anyway. It's more about opening up totally new paths. As Zhao and the team suggest, ion-based computing lets us rethink how we solve problems that traditional computers struggle with, maybe really complex pattern recognition or real-time adaptive control systems. Or even, like we touched on, in sensor computing, imagine AI processing happening right inside a camera lens or a medical sensor without having to send data back and forth. That could be revolutionary for speed and privacy.
Wow. Okay, so here's a final thought for everyone listening. If we can actually build computer hardware that learns, adapts, maybe even thinks using the same kind of ion dynamics as our own brains, what kind of truly mind-bending possibilities does that open up? Could our devices eventually, I don't know, grow their intelligence rather than just being programmed step by step? That's definitely something to chew on.